Hi everyone. So in this lecture, we will discuss the previous exam questions of Euler graph, Hamiltonian graph. Okay. So we will see all the GATE exam questions, TIFR, NET, ISRO, NIELIT, all these previous year exam questions we will discuss from this topic. From this topic, Euler graph, Hamiltonian graph. Okay. So let's start with this topic. Tell me what is the answer? So the question is from UGC NET. The question is asking, an undirected graph possesses an Eulerian circuit. Okay, Euler circuit. If and only if it is connected and its vertices are of all even degree. Yes or no? So the answer will be option A. Very simple. This we already know. So you can notice if you have a graph, if you have an undirected graph, undirected simple graph, let's assume this G, this is undirected simple graph. Okay, let's assume this graph is undirected simple graph. Then when can I say that G contains Eulerian circuit? So G contains some Euler circuit. G contains some Euler circuit. Okay, G has some Euler circuit. If and only if, what should happen? Two things should happen. The first is G must be connected. Okay, first is G must be connected. And the second, that is all vertices must have even degree. Yes or no? All vertices must have even degree. Must have even degree. Okay, so this is the idea. This is the theorem. Very simple. If G is a connected simple graph, if G is an undirected simple graph, then G contains Euler circuit if and only if it is connected and all vertices have even degree. I can also say that G is Euler graph. When can I say G is Euler graph? G is Euler graph. We can say G is Euler graph if and only if it is connected and all vertices have even degree. Okay, so very simple. So let's see this. So here you can notice undirected graph is Euler graph if and only if it is connected and all vertices are of even degree. So the answer will be option A. Now let's move on. Tell me the answer for this question. This is ISRO 2016 question. The question is asking a given connected graph is Euler graph if and only if all vertices are of, again, even degree. All vertices are of even degree. So here the answer will be option B. You can easily see that if you have a graph, if you have undirected graph, when can I say this will be Euler graph? This graph will be Euler graph if and only if it is connected and all vertices, they have even degree. Every vertex has even degree. So very simple. A connected graph is Euler graph if and only if all vertices are of even degree. So the answer will be option B. Let's see this question. This is GATE IT 2008 question. So this is a very beautiful question. Let's solve it. The question is asking, try this. So this is GATE 2008 question, a very beautiful question. Let's solve it. G is simple undirected graph. Okay, G, it is already given to you. This is the simple undirected graph. Some vertices of G are of odd degree. We add a new vertex to G, make it adjacent to each odd degree vertex. The resultant graph is sure to be. What can you say about the resultant graph? See what this question is saying. The question is saying the graph G is given to you. This is undirected simple graph. You have undirected simple graph. So this is an undirected simple graph that is given to you. Now the question is saying that in this graph, you have some even degree vertices, some odd degree vertices, right? So in this graph, this is your, I can say G, V, E. This is the set of vertices. The set of vertices is, let's assume A1, A2, and so on. So these are some vertices. Okay, let's assume these are the vertices of even degree and these are the vertices of odd degree. Okay, let's assume these are the vertices of odd degree. So you can see in this graph, you have some vertices of even degree, some vertices of odd degree. Okay, here, let me assume that these are the even degree vertices. Let's assume these are the even degree vertices. These are the even degree vertices. And let's assume these are the odd degree vertices. These are the odd degree vertices. Okay, yes or no? These are the even degree vertices. These are the odd degree vertices. Now what you are doing? Now we are adding a new node. Okay, we are adding a new vertex to this graph. This new vertex we are adding. This new vertex we are adding to this graph. And what we are doing? We are making it adjacent to each odd degree vertex. So this will be adjacent to every odd degree vertex. Okay, now you tell me. Now the question is asking, what can you say about the resultant graph? Okay, first of all, you tell me. Oh, these are already even degree vertices. Tell me, after you add this vertex, will they remain even degree vertices? I'm adding this vertex and I'm making it adjacent to every odd degree vertex. This vertex V, this new vertex V I am adding, I'm making it adjacent to every odd degree vertex. So tell me, in this new graph, you got a new graph. In this new graph also, these are even degree vertices, right? Agree? In the new graph also, these are even degree vertices. All of them are even degree vertices. Okay, correct. So all of them are even degree vertices. Now you tell me, in the new graph, these vertices, now what is the degree of this vertex? Tell me, in the new graph, what the degree of this vertex? In new graph, I'm asking, in the new graph, what is the degree of this odd degree vertex? Let me know. What is the degree of this vertex B1? Yes, this degree will become even. Okay, because you can notice in the old graph, you can easily notice in the old graph, this was the old graph. In the old graph, this B1 has odd degree. Now, what you are doing? You are making it adjacent to V. Now, this degree will become even, yes or no? So very simple. In the old graph, this is your old graph. In the old graph, this is odd degree vertex. In the new graph, what will happen? This will become even degree vertex. This will become even degree vertex. Okay, correct. Similarly, B2 will also become even degree vertex. Bn will also become even degree vertex in the new graph. Okay, in a new graph. So tell me, but can you guarantee that this will also have even degree vertex? Tell me, can you guarantee? This is my question. See, all of them have even degree in the new graph. Okay, I'm talking about new graph. In the new graph, all of them have even degree. In the new graph, all of them have even degree. But what you can say about this vertex? What you can say about the degree of this vertex? What is the degree of this vertex? Tell me. What is the degree of this vertex? Can you guarantee this will have even degree? Can you guarantee this vertex will have even degree? Can you guarantee that? Can you guarantee this vertex V, this will have even degree? Yes, we can guarantee. Why we can guarantee? Because you already know that in any simple graph, okay, in every, see this we already know, in every simple undirected graph, what happens? In every simple undirected graph, what happens? In every simple undirected graph, number of odd degree vertices is always even. In every, whatever graph you take, in every simple undirected graph, what happens? Number of odd degree vertices. Number of odd degree vertices. How many odd degree vertices you have? Number of odd degree vertices is always even. Is always even. Yes or no? This we already know. Number of odd degree vertices is always even. How many odd degree vertices you have? That is always even. So remember, in this old graph G, tell me, what can you say about this N? What you can say about this N? Tell me. What you can say about the number of odd degree vertices? N is number of odd degree vertices, right? N is number of odd degree vertices. Odd degree vertices. And that will be equal to even. N is the number of odd degree vertices and number of odd degree vertices will be even. So you can notice N is even. Now you can just come back. Now you can see the degree of V, that will be, what will be the degree of V? What will be the degree of V? That will be N, because this V is adjacent to these N vertices. This vertex V, this is adjacent to these N vertices. So I can say degree of v is n, and this n is even. So what we got? Tell me. So what we got? Did you notice in the new graph, this vertex has even degree. All these vertices have even degree. All these vertices have even degree. So in the new graph, every vertex has even degree. Yes or no? In the new graph. So what we got? We got that in the new graph. In new graph, every vertex is of even degree. Every vertex is of even degree. Is of even degree. Yes or no? Okay, in the new graph, what happened? In the new graph, every vertex has even degree. Please tell me, is this clear? In the new graph, every vertex has even degree. So here, the question is asking that you have a simple undirected graph. Some vertices are of odd degree. Add a new odd, make it adjacent to each odd degree vertex. The resultant graph is sure to be. What you can say about the answer? The resultant graph is sure to be. See, here you can notice. Tell me, is it necessary the new graph will be connected? Is it necessary the new graph will be connected? Tell me. Is this necessary the new graph will be connected? This is given to you. G is simple undirected graph. Some vertices are of odd degree. You are adding a new vertex, making it adjacent to each odd degree vertex. The resultant graph, is it necessary to be connected graph? The resultant graph, is it necessary to be connected graph? Tell me. The new graph that you will get, can you say it will be, I can say it will be a connected graph. So in the new graph, every vertex is of odd degree. But what about new graph? Is new graph necessarily a connected graph? Is new graph necessarily a connected graph? Is new graph necessarily a connected graph? Tell me, what do you think? New graph, can you say that is necessarily a connected graph? Let me tell you, the answer is no. Okay, for example, you consider this old graph. Okay, consider this graph G. Let me give you a graph G. Okay, don't worry. Just consider this graph G, A, B, C, D. And let's assume I am giving you this graph G, E, F, G, H. Let's assume this was your old graph. Okay, this was your old graph, degree 2, degree 2, degree 3, degree 3, degree 3, degree 3. Let's assume this is your old graph. Okay, let's assume this was your old graph. Is this clear? Okay, so let's assume this was your old graph. Please tell me in the question, whatever this graph, does it satisfy the conditions in the question? This graph, does it satisfy the conditions given in the question? Yes, this is a simple graph, right? See, this graph G that I have given to you, this is simple graph. Yes or no? This is a simple graph. Yes, this is a simple graph. What else? This is undirected graph. Some vertices have odd degree. Everything is fine. Yes or no? Everything is fine. Now what we are doing? We are adding a new vertex. Okay, we are adding a new vertex. Now, what will happen in the new graph? In the new graph, what will happen? What will happen in the new graph? You are adding a new vertex. Okay, what you are doing? You are adding a new vertex. Now, just focus what is happening in the new graph. In the new graph, you are adding a new vertex. I am making it adjacent to every previous odd degree vertex. Making it adjacent to every previous odd degree vertex. Now tell me in the new graph, what is the degree of every vertex? This is the new graph, degree 4, degree 4, degree 4, degree 4, and degree 4. Yes or no? So this resultant graph, this is your resultant graph. This is your resultant graph. Okay, tell me, is this Euler graph? Is this Euler graph? Tell me, this graph, is this Euler graph? Let me know. This is the resultant graph. Is this Euler graph? Is there any Euler circuit? Is there any Euler circuit? This is not Euler graph. Yes or no? This is not Euler graph. Tell me, for example, can you start at some point and then you visit every edge exactly once and then you come back to the same point? Is it possible? Tell me, is it possible that you start at some point, you visit every edge exactly once and then you come back to the same point? That is not possible. This is the new graph. This is your new graph. Okay, this is your new graph. Tell me, in this new graph, do we have Euler circuit? Is there any Euler circuit? Is there any Euler circuit? Please tell me. Is there any Euler circuit? Let me know. Can you start at some vertex? You start at some vertex. Can you visit every edge exactly once and then you come back to the same vertex? That is not possible. Is there any Euler circuit? The answer is no. So this is not Euler graph. Yes or no? This is not Euler graph. Tell me, this resultant graph, is this regular graph? Is this a regular graph? Tell me, this resultant graph, is this regular graph? This is not regular graph. Yes or no? This graph is not regular graph. You can notice here, this vertex has degree 2, this vertex has degree 4. Regular graph means every vertex has same degree. Yes or no? What is the definition of regular graph? Regular graph means every vertex has same degree. Okay, yes or no? Every vertex has same degree. Has same degree. Every vertex has same degree. So this is your regular graph. So this new graph is not regular graph. You can notice this vertex has degree 2, this vertex has degree 4. Okay, tell me, is this complete graph? This new graph that you got, is this complete graph? This new graph that you got, is this complete graph? No. In a complete graph, what happens? Tell me. In a complete graph, what happens? Let me know. What is the definition of complete graph? In a complete graph, every two vertices are adjacent. Yes or no? Every two vertices are adjacent. Every pair of vertices adjacent. Every pair of vertices, whatever two vertices you take, every pair of vertices are adjacent. Are adjacent. Here you can notice these two vertices are not adjacent. Can you notice these two vertices are not adjacent? These two vertices are not adjacent. So this is not complete graph. Tell me, is this Hamiltonian graph? Is this Hamiltonian graph? Tell me, this new graph, is this Hamiltonian graph? Let me know. This new graph. This is not Hamiltonian graph because Hamiltonian graph must be connected. Hamiltonian graph must be connected. Yes or no? You already know this point. Every Hamiltonian graph is connected. Every Hamiltonian graph is connected. So this is not a Hamiltonian graph also. Okay, so tell me, what can you say about the resultant graph? See, you can notice the resultant graph, that you cannot say it is regular. The resultant graph, the final graph, you cannot say it is regular. You cannot say it is complete. You cannot say it is Hamiltonian. You cannot say it is Euler. So what you can say about the resultant graph? What you can say about the resultant graph? So for this question, the answer will be, what is the answer? No option matches. Yes or no? There is no option that matches. So for this question, there is no option that will match. Is this clear? Please tell me. Did you understand the small points in this question? Let me know. Did you understand the small points in this question? Every small point, did you understand? Please tell me. Okay, so remember, no option matches. There is no option matches. You tell me one thing. So remember, in this question, none of them is correct answer. None of them is correct answer. None of them is correct answer. None of them is a correct answer. Okay, in this question. So, but if you are in the GATE exam, which option you will tick? Will you leave this question in the GATE exam? If you are in the GATE exam in those 3 hours, I am asking, in those 3 hours, in those 3 hours in the GATE exam, will you leave this question? Let's assume you find out you are very intelligent. Okay, you know the basic things. Okay, you understand all the some small things. Let's assume you find out that none of the option is correct. This is what you find out in those 3 hours. You find out that none of the option is correct. Then tell me, will you leave this question? Don't leave the question. Okay, whichever you think whichever is the best option. See, read the question maker's mind. Read the question maker's mind. Some professor created this question. Yes or no? See, this question is very beautiful. Some professor created this question. Okay, now that professor, what answer that professor is thinking? Please tell me. What answer that professor is thinking? Some professor created this question. That professor is thinking what answer? Okay, he is thinking Euler. Yes or no? That professor is thinking that answer is Euler. Basically, in this question, he did not mention the connected graph. That is the only problem. That is the only problem. I hope you understood. So no option matches, but this option you can tick. Okay, in those 3 hours you can tick this option. This is what I'm saying. In those 3 hours, in the gate exam, in those 3 hours, you can tick it. You can check this option. You can check this option, because I can say that read the professor's mind. The professor who created this question, that professor is thinking that this is the answer. Basically, in this question, I can say that this connected condition is missing. Which condition is missing? Tell me. A very important condition is missing. In this question, a very important condition is missing. What does that tell me? Condition missing, that is connected. This connected condition is missing. If you put this condition, then answer will be option D. This condition is missing. Okay, in the same question, if I put this condition, then the answer will be option D. But I hope you understood. So don't leave this question. In those 3 hours, don't leave. Okay, don't leave a question. Don't leave the question. Is this clear? In those 3 hours, don't leave the question. Read the question maker's mind, I can say. Read question maker's mind. What question maker was thinking? Probably question maker's mind. Okay, so you can notice this condition is missing, connected. This condition is missing. So in those 3 hours, you can check this option. This option you can check in those 3 hours. But remember, is this option correct? For this question, option D is correct or not? For this question, option D is not correct. Option D, that is not correct. Not correct. The question is asking sure to be. See, read this. The resultant graph is sure to be. So this option D is not correct. But this is, I can say, this is what question maker is thinking. The professor who created this question, that professor is thinking that option D is the answer. Okay. So I hope you understood this. So in this same question, remember, if I change the question and if I say that simple undirected connected graph, if I change the question, if I add this condition, okay, if I add this condition that G is simple connected undirected graph, now what will be the answer? Now what will be the answer? Tell me, now what will be the answer? Now there is no confusion. The answer will be option D. Now option D is correct answer. Now option D is a correct answer. Okay. So I hope you understood. So that is the reason I said that this is beautiful question. Okay. But let me tell you what students do. See, majority of the students who will solve this question, they will not consider these small things. See, whenever you have Euler graph, then you have to make sure what? Tell me. Whenever you have Euler graph, you have to make sure that it is connected, and that it has even degree vertices. Even degree vertices, right? Yes or no? All even degree vertices, all even degree vertices, right? Yes or no? So these two things you have to make sure. See, this question can become very tricky if there is none of these is the option. Just think about it. If one of the option, let's assume this condition is not given, let's assume this condition is not given, and one option is none of these. Okay, just think about it. Let's assume option A is none of these. Now this question will become very tricky. Yes or no? Let's assume option A is none of these. Now this option A will be the answer. Okay, remember, now option A will be the answer. Now there is no confusion. Option A will be the answer. Okay, I hope you understood all these small points. So remember, for Euler graph, you have to make sure it is connected as well as all even degree vertices. See, what you can do. See, isolated vertices you can be fine. Yes or no? See, for isolated vertices you can allow. Isolated vertices you can allow, but you cannot allow these type of things. For example, this counter example I gave you. Yes or no? I gave you this counter example. So isolated vertices you can allow, but you can see that this type of disconnected graph you cannot allow. This type of disconnected graph you cannot allow. Okay, so this is the answer. So I hope you understood. Let's move on now. Now let's see this question. So let's solve this question. This is UGC NET Computer Science question, August 2016. Given the following graph, two graphs are given to you, G1, G2. The question is asking which of them contain Euler circuit and which of them do not contain Euler circuit. So tell me, what is the condition for Euler circuit? What is the condition for Euler circuit? Remember, tell me, these are simple graph or multi-graph? Tell me, these are simple graph or multi-graph? Remember, these are multi-graph. Okay, these are multi-graph, but the condition is same. You can notice these are multi-graph. If you notice, just notice this graph. If you notice, this is a multi-graph. This is a multi-graph. Why this is a multi-graph? Because you can notice between B comma E, there are two edges. You can notice between E comma C, there are two edges. So this is actually multi-graph. This is not a simple graph. Okay, but that is fine. That is fine. This condition will hold for multi-graph also. So I can say if your G is undirected multi-graph, if your G is undirected multi-graph, if your graph is undirected multi-graph, then when can I say G is Euler graph? When can I say G contains Euler circuit? G has some Euler circuit. When can I say G has some Euler circuit? If and only if it is connected and every vertex has even degree. Yes or no? If and only if G is connected and every vertex has even degree. Every vertex has even degree. Every vertex has even degree. Okay, so very simple. This is the idea. So G has some Euler circuit if and only if it is connected and every vertex has even degree. This will work for multi-graph also. The same thing, this theorem, this result, this will work for multi-graph also. So let's see this. So for this question, tell me, these are connected graph. G1 is also connected. G2 is also connected. Yes or no? G1, G2 both are connected. You can notice. So tell me, what about G1? In G1, what is the degree? In G1, you can notice this vertex B. What is the degree of vertex B? That is 3. Yes or no? So G1 does not have Euler circuit. G1 does not have Euler circuit. This vertex B, this has degree 3. This vertex E, this has degree 3. This vertex A, this has degree 3. Yes or no? This vertex C, this has degree 3. This vertex has degree 2. So you can see G1 does not have Euler circuit. What about Euler path? What about Euler path? So G1, just focus on G1. G1 has no Euler circuit. What about Euler path? G1 has no Euler circuit. What about Euler path? There is no Euler path also. There is no Euler path also. For Euler path, what must happen? For Euler path, what must happen? Tell me. For Euler path, what must happen? You know that Euler path must, if you want Euler path, then what must happen? That it must be connected and exactly two vertices must have odd degree. For Euler path, what must happen? This must happen that you must have connected graph. You must have connected graph and number of odd degree vertices must be 2. Exactly 2 vertices of odd degree. Exactly 2 vertices of odd degree. Vertices of odd degree. Exactly 2 vertices of odd degree. Yes or no? So you can notice here you have 4 odd degree vertices in this G1. In this G1, you have 4 odd degree vertices. This is odd degree, odd degree, odd degree, odd degree. So I can say there is no Euler path. There is no Euler circuit. Because there is no Euler circuit, so I can say this is not Euler graph. Yes or no? So I can say this is not Euler graph. This graph G1 is not Euler graph. So here you can notice G1 does not contain Euler circuit. So I can say option A is gone. Okay, option A is gone, option D is gone. Now let's check this next graph G2. What about G2? Tell me. What about this graph G2? You can notice what is the degree of vertex B? The degree of this vertex B, that is 4. Degree of D, that is 3. So again, there is no Euler circuit. See, degree of vertex D, that is 3. So no Euler circuit. So I can say answer will be option C. There is no Euler circuit. In this G2 also, there is no Euler circuit. There is no Euler circuit. Why there is no Euler circuit? Because you can notice this vertex has degree, odd degree. This vertex has odd degree. So you don't have any Euler circuit. So the answer will be option C. Okay. G1, G2, they do not contain Euler circuit. So the answer will be option C. But anyway, what about Euler path? What about Euler path? What about Euler path in this G2? You can notice vertex A, this at degree 3, vertex C, this at degree 4, and vertex E, that is degree 6. So exactly two vertices have odd degree. Yes or no? Can you notice exactly two vertices have odd degree? So I can say Euler path exists. Euler path exists. But you can notice because there is no Euler circuit, so this is not Euler graph. This graph is not Euler graph. This graph is not Euler graph. Let's move on now. So this question we have seen. The answer will be option C. Now let's see. Let's solve this question. This is TIFR 2020 question based on Euler cycle, Hamiltonian cycle. So let's solve this question. So the question is asking, G is undirected graph that is given to you. Okay, G is undirected graph. An Euler cycle of G is a cycle that will cross every edge exactly once. Okay, this is the definition of Euler cycle, or I can say Euler circuit. Okay, basically visit every edge exactly once. What is Hamiltonian cycle? Hamiltonian cycle is a cycle that will visit every vertex exactly once. This we already know. We know what is Euler cycle. We know what is Hamiltonian cycle. Euler cycle means Euler circuit. Okay. Which of the following must be true? The question is asking, which of the following must be true? Tell me the first one. Checking if G has Euler cycle can be done in polynomial time. Is this true? Checking if G has Euler cycle can be done in polynomial time. Yes, this is true. Yes, this statement is true. We already know. What is the time complexity? If this graph is given to you, if this graph V, G, V, comma E, if this graph is given to you, what is the time complexity? Time complexity to check if G is Euler graph or not. If G is Euler graph or not. If G is Euler graph or not. All you have to do, tell me what you need to do. You just need to find the degree of every vertex. For this, what you need to do? Two things you have to do. First, you have to check connected. Agree with me? First, you have to check connected. This graph is connected or not. First, you have to check connected. How much time it will take? First, you have to check connected. How much time it will take? You can apply BFS, DFS, some algorithm you can apply. Yes or no? So, here the time complexity will be order of V plus E. You can apply what you can apply? You can apply DFS. You can apply DFS because this is undirected graph. This graph is undirected graph. It is already given to you. This is undirected graph. You can apply DFS. Yes or no? Agree with me? So the time complexity will be order of V plus E. What then? Second thing, what you will check? First, you will check connected. Then you will check degree. Then you will check degree. Check degree is even for every vertex. For every vertex. Check degree is even for every vertex. For that, how much time? Again, order of V plus E. Again, order of V plus E. Because what you need to do? You need to check degree of every vertex. Whatever vertex you have, for example, if you have these vertices V1, V2, V3, and so on, Vn. If you have these vertices, then what you have to check? Let's assume this vertex is like this. This vertex is like this. This vertex is like this. Then what you have to do? For this vertex, you will check the degree. Okay. Then for this vertex, you will check the degree. Then for this vertex, you will check the degree. So overall, how much time you will take? Please tell me. Order of V plus E. For every vertex, you will check the degree. For every vertex. So this is for vertices. For every vertex, you will check. And for one vertex, how much time you will take? For one vertex, how much time you will take? For one vertex, this is the time you will take. This is the time you will take. So total, for this vertex V3, this is the time you will take. For this vertex V1, this is the time you will take. For this vertex V2, let's assume this is your V2. So for this vertex V2, this is the time you will take. This is the time you will take. So overall, I can say order of V plus E. Remember this point. You can notice that order of 2E, that is same as order of E. Okay, order of 2E, that is same as order of E. So I can say overall, this is the time you will take. Order of V plus E. So here also order of V plus E. So finally, I can say, you can see what is the time complexity? That is order of V plus E. That is polynomial. That is polynomial. Yes or no? That is polynomial. So tell me one more thing. If you have a complete graph, then this will become order of n square. Yes or no? If you have a complete graph, then this will become order of v square. If this is a complete graph, but overall this is polynomial. I can say this is polynomial time. This is polynomial time. Okay. For example, if you have a complete graph, then this will become v square. Then this will become v square. If you have complete graph, then number of edges will be v square, something like that. Yes or no? Order of v square. So I can say overall you have polynomial time. So I can say option A is correct. What about option B? Deciding if G has Hamiltonian cycle is not NP complete. No, this is NP complete. This is NP complete problem. Okay, this is NP complete problem. Remember, if you have a given graph has Hamiltonian cycle or not, that is NP complete problem. This Hamiltonian problem, let me tell you, this Hamiltonian problem, given graph has Hamiltonian cycle or not, that is NP complete problem. This we have seen in our lectures. Yes or no? This we have already seen in the lectures. This is NP complete problem. Let me tell you, this NP complete, what is NP complete, what is NP hard, that is not in the syllabus. This is not in GATE syllabus. This is not in the GATE syllabus. But this question is not from GATE exam. This is question from TIFR. Yes or no? This is not in the GATE syllabus. This, what is NP complete, what is NP hard, that is not in the GATE syllabus, but this is a TIFR question. Anyway, you can see this is NP complete problem. So this is gone. What about this one? If G has Euler cycle, then it has Hamiltonian cycle also. Is this true? If G has Euler cycle, then it has Hamiltonian cycle also. Is this true? This is not true. There is no relationship between Euler cycle and Hamiltonian cycle. Agree with me? There is no relationship between Euler cycle, Hamiltonian cycle. For example, for option C, you consider this graph. Just consider this graph A, B, C, D, E. Consider this graph. Very simple graph you can consider. This graph you consider. In this graph, you can notice degree 2, degree 2, degree 4, degree 2, degree 2. This graph is connected. This graph is connected. Also, every vertex has even degree. So this is Euler graph, yes or no? This contains Euler cycle, correct? This contains Euler circuit, or I can say Euler cycle. So tell me, is this Hamiltonian graph? Is there any Hamiltonian cycle in this graph? In this graph, do we have any Hamiltonian cycle? For example, if I start here, can I come back here? If I start here, visit every vertex exactly once. If I start here, visit every vertex exactly once, then can I come back? Visit every vertex exactly once. I cannot visit it again. I cannot visit this vertex again. You cannot visit this vertex again. So if I start here, I cannot visit it again. I cannot visit here. I cannot visit again. So is there any Hamiltonian cycle? There is no Hamiltonian cycle. You can check. You can check. There is no Hamiltonian cycle. If I start here, can I come back to C? Can I come back to C? You cannot visit vertex again. You cannot visit any vertex more than once. So you can see whatever you do. If I start here, then also, can I come back again? I cannot come back. So there is no Hamiltonian cycle. Okay. I told you one thing in the lectures, that there is no relationship between, you can see, there is no relationship between Euler graph, I can say Euler circuit, and Hamiltonian cycle. Yes or no? This I told you, there is no relationship. Everything is possible. For example, okay, for example, Euler circuit, Hamiltonian cycle. This is possible that you have both of them. This is possible. Yes or no? This is possible that you have both of them. You have both of them. That is possible. Give me a graph in which you have both of them. Give me a graph in which you have both of them. For example, consider this graph. Consider this graph. In this graph, you have both of them. In this graph, you have Hamiltonian cycle also. You have Euler circuit also. Okay. This is also possible that you have none of them. This is also possible you have none of them. Okay, this is also possible. You have none of them. For example, you consider this graph. Consider this graph A, B, C, D, E, and just make it F. Now you can notice this vertex has odd degree, this vertex has odd degree, even degree, even degree, even degree, odd even degree. Now you can notice there is no Euler circuit. There is no Euler circuit because you have odd degree vertex. Okay, there is no Euler circuit. You can notice there is no Hamiltonian cycle also. There is no Hamiltonian cycle also. Okay, or you can do like this, or you can take a disconnected graph, or you can take a disconnected graph. For example, consider this graph. For example, consider this graph. In this graph, you can notice this graph you consider A, B, C, D, E, F, G. In this graph, there is no Euler circuit. There is no Hamiltonian cycle. Okay, so this is also possible. You don't have any of them. This is also possible. You have this. You don't have this. Okay, you have Euler circuit. You don't have Hamiltonian cycle. This is also possible. For example, this graph. In this graph, you have Euler circuit, but you don't have Hamiltonian cycle. And this is also possible that you don't have Euler circuit, but you have Hamiltonian cycle. This is also possible. Can you give me graph? Can you give me a graph in which you have Hamiltonian cycle, but you don't have Euler circuit? Yes, you can give this graph. This K4 you can give. You can give this K4, A, B, C, D. This vertex at degree 3, degree 3, degree 3, degree 3. Every vertex at degree 3. This graph, there is no Euler circuit. In this graph, there is no Euler circuit, but there is Hamiltonian cycle. Yes or no? So you can take this graph K4, complete graph on 4 vertices. So you can see, do you agree? There is no relationship between them. Do you agree? There is no relationship between Euler circuit and Hamiltonian cycle. There is no relationship. Everything is possible. Yes or no? Everything is possible. Agree with me? So you can easily see. Okay. You can also take, for example, you can also take K5. Here, you can also take K5. Can you take K5? You cannot take K5. See, in the K5, every vertex has even degree. So you have Euler circuit and you have Hamiltonian cycle also. Yes or no? In K5, every vertex has even degree. In K5, every vertex has even degree. Yes or no? Every vertex has even degree. In K5, every vertex has even degree. So this K5 has Hamiltonian cycle also, Euler circuit also. Okay, so I hope you understood all these things. So you can see there is no relationship between Euler circuit and Hamiltonian cycle. Okay, let's move on now. What about option D? Tell me. What about option D? So you can notice option C is wrong. Option C is false. What about option D? A complete graph always has both Euler cycle and Hamiltonian cycle. No. What the counterexample? What the counterexample? Tell me what the counterexample you can give. The counterexample is K4. You can give the counterexample, that is K4. In K4, there is no Euler circuit. But yes, there is Hamiltonian cycle. Can I say yes or no? Can I say? So you can notice in this K4, there is no Euler circuit. Okay, but there is Hamiltonian cycle. Can I say complete graph always has Hamiltonian cycle? This statement can I say? Can I say complete graph always has Hamiltonian cycle? Can I say? Tell me. This is my question. Can I say complete graph always has Hamiltonian cycle? Complete graph always has Hamiltonian cycle. Tell me the answer. Here the answer is, what the answer? Here the answer is no. Why? For example, your K2 is the counterexample. Consider this K2. This complete graph on 2 vertices. Consider this. Is there any Hamiltonian cycle? Is there any Hamiltonian cycle? Can you give me Hamiltonian cycle here? Can you give me Hamiltonian cycle? You start at some vertex, you visit every vertex exactly once, and then you come back. Tell me. Let me know. Is there any Hamiltonian cycle? There is no Hamiltonian cycle here. Yes or no? Here there is no Hamiltonian cycle. I hope you understood. But I can say, this statement I can say, complete graph with at least 3 vertices. Complete graph with at least 3 vertices. Complete graph with at least 3 vertices always has Hamiltonian cycle. Always has Hamiltonian cycle. Yes, that is correct. This statement is true. This statement is true. Is this clear? Please tell me. See, complete graph with at least 3 vertices. If you have a complete graph with at least 3 vertices, then it will always have Hamiltonian cycle. That is true. For example, let's see. If you have a complete graph, let's assume you have a Kn. You have a complete graph where n is greater than equal to 3. Okay. So in this Kn, let's assume this is your Kn. Vertices are these. These are the vertices. A1, A2, A3, A4, and so on, An. Okay. Where number of vertices is greater than equal to 3. Can you create Hamiltonian cycle? Can you create Hamiltonian cycle? Tell me. Can you create Hamiltonian cycle? Create Hamiltonian cycle here. Yes, you can create. For example, you can start at A1. You can start at vertex A1. Tell me, is it necessary that you have edge between A1 and A2? Is it necessary? Is it necessary that you have edge between A1 and A2? Yes, because it is complete graph. Between every 2 vertices you have edge. Every 2 vertices are adjacent. Is it necessary there is edge from A2 to A3? Is this necessary? Is this necessary? Yes, this is necessary. Yes or no? Because this is complete graph. Between every 2 vertices you have edge. Every 2 vertices are adjacent. So like this you keep going on. Okay, is it necessary you have edge between these 2? Is it necessary you have edge between these 2? Yes, because it is complete graph. Between every 2 vertices you have edge. Okay, so yes or no? So this is your Hamiltonian cycle. So I can simply say that Kn, where n is greater than equal to 3, that will definitely have Hamiltonian cycle. Okay, but you can easily notice, remember, your K4, you can take K4, you can take K6, you can take K even. Okay, you can take K even, where this is greater than equal to, I can say, where greater than equal to 4. Okay, you can take K even. So in these graphs, what will happen? Tell me. In all these graphs, what will happen? What will happen in all these graphs? What will happen? There is no Euler circuit. You have no Euler circuit because every vertex has odd degree. In this also, every vertex has odd degree. So there is no Euler circuit, but there is Hamiltonian cycle. There is Hamiltonian cycle. So you can easily see that option D, that is also wrong. Option C is wrong. Option B is wrong. Option A is correct. All statements are true. This is also wrong. So what is the answer for this question? The question is asking what must be true. The answer will be option A. Is this clear? This is your TIFR 2020. Okay. So simple. Yes or no? Agree? So let's move on. So you can see this point is important. In this question, actually, option C is interesting. In this question, option C is interesting. This option C, remember, there is no relationship between Hamiltonian cycle and Euler cycle. You can notice. Hamiltonian cycle, Euler cycle, there is no relationship. For example, in this graph, you have both of them. In this graph, you have Euler cycle, but you don't have Hamiltonian cycle. In this graph, you have Hamiltonian cycle, but you don't have Euler cycle. In this graph, you have none of them. Okay, so there is no relationship between these two. There is no relationship between these two. All the things are possible. Everything is possible. Okay, you can also take this counter example. For example, for option C is saying if G has Euler cycle, then G has Hamiltonian cycle. You can also take for counter, you can say for option C, what counter example you can take? You can also take C count. Let me give you one more counter example for option C. For option C, you can take this K24. You can take this complete bipartite graph. You can take this complete bipartite graph K24, B1, B2, B3, B4. You can take this also. Okay, this complete bipartite graph also you can take. Tell me, in this graph, do we have Hamiltonian, do we have Euler cycle? Do we have Euler circuit? Let me know. Do we have Euler circuit in this graph? You can notice degree here 4, degree 4, degree 2, degree 2, degree 2, degree 2. So yes, there is Euler circuit. This is connected also. Okay, so this is connected also. You can notice. This is connected also. Every vertex even degree. Every vertex even degree. So I can say what I can say from these two. I can say that yes, there is Euler cycle. Euler circuit exists. What about Hamiltonian cycle? Is there any Hamiltonian cycle here? In this graph, do we have Hamiltonian cycle? Simple question. Is there any Hamiltonian cycle? You can check. There is no Hamiltonian cycle. You can check. You can check it. For example, if you start here, then can you come back to vertex A1? See, you start here. Can you come back to this vertex? But remember, you have to visit every vertex exactly once. Okay, so you start here, you go to B1, you go here, you go here. Now you cannot visit them. Yes or no? Now you cannot visit them. Agree with me? See, if you start here, you go here, you go here, you go here. Now you cannot visit these two vertices. If you start here, you go here, you go here, you go here, you go here. Now you cannot visit this vertex. So very simple. There is no Hamiltonian cycle. Okay, so let's move on now. So you can see in this graph, in this K24, this graph has Euler circuit, but there is no Hamiltonian cycle. In this graph, we don't have a Hamiltonian cycle. Let's move on now. Let's see this question. This is another TIFR question, TIFR Computer Science 2016, question number 9. So let's see this. Which of the following graph, the question is asking, which of the following graph does not have Euler circuit? Which of the following graph does not have Euler circuit? Recall that Euler circuit in undirected graph is a walk that starts at a vertex, returns to the vertex after traveling every edge exactly once. Okay, so the definition of Euler circuit is also given to you. Now tell me, which of these graphs do not have Euler circuit? For Euler circuit, what you need? If you want Euler circuit, then what you need? Tell me. If you want Euler circuit, what do you need? In any undirected graph, let's assume G is undirected graph. Let's assume this graph G, this is undirected graph. Then G has Euler circuit. I can say G has Euler circuit. When can I say G has Euler circuit? G has Euler circuit if and only if G must be connected. G must be connected. Okay, there can be isolated vertices. That is fine. See, isolated vertices is not a big problem. Okay, so remember G must be connected, but possibly you can have isolated vertices. Isolated vertices are fine. There is no problem with isolated vertices. But anyway, let's not worry about it. So let's see. G has Euler circuit if and only if it is connected and every vertex even degree. Every vertex has even degree. Have even degree. So these two things you have to check. You have to check these two things. Remember, this graph has Euler circuit if and only if it is connected and every vertex has even degree. You have to check these two things. So let's start with the option A. Let's start with option A. K99. What about this one? This is your complete bipartite graph. Yes or no? This is your complete bipartite graph. This is your complete bipartite graph. Is this connected? This K99, is this connected? This is your complete bipartite graph. A1, A2 and so on A9. B1, B2 and so on B9. Okay, this is your complete bipartite graph. This type of graph you have. Okay, this type of graph you have. This is your complete bipartite graph. So like this graph you have. This is your, remember, this is your K99. Now you tell me, in this, what is the degree of every vertex? See, what is the degree of this vertex? Tell me, what is the degree of this vertex? Degree of this vertex is 9. Every vertex at degree 9. Yes or no? Degree of this vertex is also 9. Degree of this vertex is also 9. So in this graph, every vertex at degree 9. Every vertex has a degree equal to 9. And that is odd. And that is odd. So I can say this graph definitely does not have Euler circuit. Yes or no? This K99, there is no Euler circuit. There is no Euler circuit. This graph has no Euler circuit. Tell me, is this connected? Was this graph connected? Yes, this graph is connected. This K99, yes, this graph is connected. You can check. This graph is actually connected. Between every two vertices, you have path. Between every two vertices, there is path. For example, B1, B2, there is path. This is the path. Okay. Between these two vertices also, there is a path. Between A1, A2, there is a path. Between every two vertices, there is a path. So yes, this is connected, but there is no Euler circuit. The question is asking, which does not have Euler circuit? Which does not have Euler circuit? So the answer will be option A. Yes or no? Answer will be option A. What about K88? What about this graph? K88. What about this graph? Now the next graph is K88. Tell me, K88. Here you can notice you have how many vertices you have? Tell me. So you have K88. It's like A1 to A8 and B1 to B8. So here this vertex at degree 8. And also you can note this vertex at degree 8. Every vertex at degree 8. Every vertex at degree 8. Okay, and that is even. Okay, so yes, there is Euler circuit. So I can say in this K88, that is connected also. That is connected also. Every vertex has even degree also. So yes, there is Euler circuit. There is Euler circuit. So I can say, yes, there will be Euler circuit here. Yes or no? The question is asking does not. The question is asking does not. So tell me, if this is MCQ question, can you stop here? If this is MCQ question, if this question is MCQ, can you just say that answer is A and then move on? Yes or no? If this question is MCQ, you can say answer is A and you can move on. Yes or no? Actually, this question is MCQ. In the TIFR question, all questions are MCQ. Every question is MCQ. Okay. So you can see, you can stop here and you can move on. But anyway, the point is, this has no Euler circuit. There is no Euler circuit. This has Euler circuit. This has Euler circuit. What about K12? This also has Euler circuit. Yes or no? And what about K9? This is complete graph on 9 vertices. This is complete graph on 9 vertices. What about K9? Tell me. What you can say about K9? This is your complete graph. This is your complete graph on 9 vertices. On 9 vertices. So this is your complete graph. A1, A2, A3, and so on, A9. Tell me what is the degree of this vertex? Remember, this is complete graph. Remember, this is complete graph like this. Okay, this is a complete graph. Every two vertices are adjacent. This is a complete graph. So what is the degree of every vertex? This vertex is adjacent to every other vertex. This vertex A2, that is adjacent to every other vertex. So here the A2 has degree equal to 8. This vertex also has degree equal to 8. So this is connected also. So I can say this graph, this is connected. Also, every vertex has even degree. Every vertex has even degree. So I can say, yes, this graph has Euler circuit. This graph has Euler circuit. There is Euler circuit. Yes or no? This is your K9. Okay. What about, so here I can say here there is Euler circuit. This has Euler circuit. What about the next graph? Option E. Let's focus on option E. The graph G with vertex set 1 to 9 and with edge set. This edge set is given to you. Okay. So this graph is given to you. Let's see the graph. Let's see this graph. So let's see option E. So what this graph is saying. Just take your copy pen. Can you take your copy pen for this graph? The graph which has 9 vertices. There is graph that has 9 vertices. Okay, you have number of vertices, that is 9. These are the vertices. V equal to 1, 2, and so on 9. These are the vertices. Now, what are the edges? The question is saying, what are the edges? You have edge. This is the set of edges. You have edge between I, comma j. When can I say there is edge between I, comma j? You have edge between I, comma j. There is edge between I, comma j. Okay, because this is undirected. So this is undirected, right? So there is edge between I, comma j. If this happens, or this happens, means I can say either this happens that I is less than j, they are both less than equal to 5, greater than equal to 1. Either this should happen, or what should happen? I is less than j, both are greater than equal to 5 and less than equal to 9. Okay, so this is given to you. This is given to you. You can check. Now tell me one thing. Do we care about the graph or do we care about two things? Is it connected and what is the degree? Yes or no? Tell me, what do we care about? Just tell me. We care about, is this connected, right? Yes or no? This is what we have to care. Is this connected? And the second, we have to care about degree. Agree with me? Yes or no? We only care about these two things. So tell me, will you create the entire graph? Will you create the entire graph? This graph, will you create this entire graph? No, you don't have to create the entire graph. Just check, is it connected and what is the degree? Okay, so this is what you have to do. Okay, so let's see, can you notice this vertex 5? Notice this vertex 5. If I want to check connected, then I can start with vertex 5. Yes or no? See, let's check connected. Let's check connected or not. Please notice. Let's check connected or not. First, let me check this. Is this graph connected or not? Tell me one thing. This vertex 5, this is adjacent to whom? See, before checking this, let's make sure that you understand the question. Before checking anything, let's make sure you understand the question. Okay, see, vertices you understood, right? These are the vertices. Vertices are A, 1, 2, 3, 4, okay, 5, 6, 7, 8, and so on, 7, 8, 9. Yes or no? These are the vertices. You understood the vertices. These are the vertices. Now let's understand the edges. Let's understand the edges. See, there is edge between I, j. If either this happens or this happens. Okay, either this happens or this happens. There is edge between I, j. If this happens or this happens. So tell me, is there edge between 1, 5? Is there edge between 1, 5? Simple question I'm asking. Is there edge between 1, 5? Is this condition satisfied by 1, 5? Is this condition satisfied by 1, 5? Yes. So between 1, 5 there is edge because this condition is satisfied. Yes or no? See, this condition will be satisfied by which vertices? Tell me. This condition will be satisfied by which vertices? Which vertices? You can consider these vertices 1, 2, 3, 4, 5. Okay, you can consider these two vertices. These vertices you can consider. And this condition will be satisfied. This condition. For this condition, which vertices you will check? For this condition, you are checking 1 to 5. And for this condition, you are checking 5 to 9, 5, 6, 7, 8, 9. Yes or no? Agree with me? Please tell me. Okay, so very simple. So this condition, for this condition, you will check vertices 1 to 5. For this condition, you will check vertices 5 to 9. Okay, so let's check vertices 1 to 5. Is there edge between 1, 2? Is there edge between 1, 2? Yes, this condition is satisfied. You can take I equal to 1. You can take j equal to 2. This condition is satisfied. So there is edge between 1, 2. What about 1, 3? What about 1, 3? Yes, you can put I equal to 1. You can put j equal to 3. I equal to 1, j equal to 3. This condition is satisfied. So there is edge between 1, 3. Yes or no? There is edge between 1, 3. What about 1, 4? What about 1, 4? Yes, you can put I equal to 1. You can put j equal to 4. I equal to 1, j equal to 4. This condition is satisfied. So there is edge between 1, 4. There is edge between 1, 4. Yes or no? Can you notice one thing? Here you will get a complete graph or not? Tell me. Now can you observe? Here you are getting a complete graph because 2 will be adjacent to 3. Why? Tell me. Why 2 will be adjacent to 3? Why 2 will be adjacent to 3? Because you can take I equal to 2. You can take j equal to 3. I equal to 2, j equal to 3. So again, this condition is satisfied. So there is edge between 2, 3. There is edge between 2, 3. There is edge between 2, 4. There is edge between 2, 5. There is edge between 3, 4. There is edge between 3, 5. There is edge between 4, 5. Yes or no? Agree with me? So actually, if you notice, similarly, what will happen? Similarly, here also you will get a complete graph. Notice. Are they adjacent? 5, 7. Are they adjacent? 5, 7, 5, 7. Are they adjacent? 5, 7? Yes. You can take 5 equal to I and you can take 7 equal to j. You can take I equal to 5, 7 equal to j. So this condition is satisfied. This condition is satisfied. So yes, they are adjacent. What about 5,9? What about 5,9? Yes, you can take I equal to 5. You can take j equal to 9. So this condition is satisfied. So I can say there is age between them also. So there is age between 5, 6, 5, 7, 5, 8, 5, 9. Correct or not? So like this. And tell me, what about 7,9? What about 7,9? Yes, you can put I equal to 7. You can put j equal to 9. So this condition is satisfied. So I can say there is age. Can you notice here also you will get a complete graph? Here also you will get a complete graph. Agree? Please tell me. Yes or no? Okay. What about 3,6? What about 3,6? What about 3,6? Tell me. What about 3,6? 3,6. Will they satisfy this condition? 3,6. 3,6. Will they satisfy this condition? If I take 3,6, will they satisfy this condition? Very simple question I am asking. I am asking 3,6. Will they satisfy this condition? For example, if I put I equal to 3 and j equal to 6, is this condition satisfied? No. Is this condition satisfied? No. Yes or no? So here you can notice no condition satisfied. No condition satisfied. Yes or no? No condition satisfied. Is this clear? Please tell me. None of these condition is satisfied. So I can say they are not adjacent. Did you understand? Actually, this is the graph you got. This is the graph you got. So you can notice this graph is like this. Here you have a complete graph. If you notice what is happening here, see here you have a complete graph and here you have a complete graph, and they are, and this 5 is joining them. Okay, this 5 is the I can say bridge connection between both of them. Yes or no? This 5 is the connection between both of them. See, you have this graph, there is this graph, and you can notice there is this graph. Okay, and 5 is connecting both of them. So anyway, what about this? Is this connected? Is this connected? Is this connected? Yes, this is connected. Yes, this is connected. Yes or no? Now, so you can see, first you are checking, is this connected? Yes, this is connected. First you will check, is this graph connected? This is what you will check first. Yes, this graph is connected. Okay, see, this graph is connected. You can check in another way also. You can easily notice that these vertices are adjacent. See, these vertices, 1, 2, 3, 4, these vertices. You can see that they are adjacent through 5. Yes or no? These are adjacent through 5. There is path through 5. Agree with me? There is path through 5. There is path through 5. There is path through 5 like this. Okay, there is path through 5 like this. Okay, so anyway, the point is, yes, this is connected. Okay, this will be connected. You have path through 5. Okay, there is path between them also. There is path between them also. So anyway, you understood. This is the graph. In this graph, you can notice this is connected. What about the degree? What about the degree? Tell me. What about the degree? Tell me, what is the degree of vertex 1? What is the degree of vertex 1? Let me know. Let's find out the degree. Just check the degree now. Just find out degree. So here you can notice the degree of this vertex is 4. 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 Degree of this vertex is 8. Degree of this vertex is 8. Again, degree of this vertex is 4. Degree of this vertex 4. Degree of this vertex 4. Degree of this vertex 4. So degree is also even. So this graph is connected also. This graph is connected also. And this graph has even degree also. This graph has even degree also. All even degree vertices. Okay. So I can say, because of these two, what I can say this is, there is Euler circuit. Yes or no? Euler circuit exists. Euler circuit exists. So very simple. So for this question, you can notice the answer will be option A, because the question is asking does not. All the remaining graphs, they are Euler graph. All of them, they are Euler graphs. So for this question, the answer will be option A. I hope you understood. Okay. So this is another very simple question. So let's move on now. So this question we have seen. This TIFR question we have already seen. Let's see the next. What is the answer for this question? This is NIELIT 2017 question. NIELIT Scientist B 2017 question. Tell me, which of the following statement is or are true? The existence of Euler circuit implies the existence of Euler path. Is this true? The existence of Euler circuit implies existence of Euler path. This is false. Why this is false? Tell me. Why this is false? See, for Euler circuit, you need, what are the number of vertices you need? See, if you have a connected graph, see, very simple. Let's assume G is connected graph. Let's assume G is connected undirected graph. Okay, let's assume G is connected undirected graph. Now you tell me, for Euler circuit, if you want Euler circuit and if you want Euler path, a simple question I'm asking, if you want Euler circuit, then number of odd degree vertices, how many? Number of odd degree vertices should be how many? Number of odd degree vertices should be equal to what? That should be equal to 0. And number of even degree vertices, that should be equal to what? Sorry, in this Euler path, number of odd degree vertices should be equal to what? Number of odd degree vertices here, that should be equal to 2. So remember, for Euler circuit, the number of odd degree vertices should be 0. For Euler path, the number of odd degree vertices should be 2. So can they happen together? These two things, can they happen together? These two things, can they happen together? See, if you want Euler circuit, number of odd degree vertices should be 0. If you want Euler path, number of odd degree vertices should be exactly 2. These two things, can they happen together? Can it happen together? That number of odd degree vertices is 0 also, and number of odd degree vertices is 2 also. Can they happen together? These two things can never happen together, yes or no? If this happens, then this cannot happen. And if this happens, then this cannot happen. These two things can never happen together. Is this clear? These two things can never happen together. Number of odd degree vertices, if that is 0, then it cannot be 2. If number of odd degree vertices is 2, then it cannot be 0. So you can see these two things, they cannot happen together. So I can say for this question, S1, S2 both are false. Is this clear? Please tell me. Let me know. Is this clear? S1, S2 both are false. See, you can take this example also if you want. Consider this example. A, B, C, D. Consider this example. Is there Euler circuit? Give me Euler circuit in this graph. In this graph, give me Euler circuit. You can give me A, B, D, C, A. You can give me Euler circuit. So Euler circuit exists. Is there any Euler path? Is there any Euler path? Is there any Euler path? See, if you give me this path, if you give me this path, then what is the problem in this path? If you give me this path, what is the problem in this path? This edge is not covered. In this path, you can notice this edge AC is not covered. This AC edge, that is not covered. Yes or no? This edge AC, that is not covered. Is this clear? Please tell me. So you can easily notice that very simple point, that these two statements both are false. Both are false. Is this clear? Okay. Let me tell you one more thing. Do you remember this question is actually author dependent? Do you remember? I told you this question is actually author dependent. See, there are few authors. There are few authors who consider, there are few authors, what they consider? There are few authors, they consider that Euler path is also, Euler circuit is also Euler path. I told you this. There are few authors, what they say? They say that Euler circuit is Euler circuit, but Euler path is also Euler circuit. So, Euler circuit is Euler circuit, but every Euler circuit is also Euler path. Okay, there are few authors, what they consider? They consider that every Euler circuit is also Euler path. Is also Euler path. See what I'm saying? See, there are few authors, they say that Euler path can be open or closed. Euler path can be open or closed. See, if it is open, that is fine. If it is closed, it will become Euler circuit. Agree with me? Yes or no? See, there are few authors, they say that Euler path can be open or closed. If this is closed, If this is closed, it will become Euler circuit. So you can notice every Euler circuit is also Euler path. So according to these authors, this statement becomes true. According to these authors, this statement becomes true. This statement will still be false. This statement will still be false. Okay, what is the counter example? This statement will still be false. For example, you can consider this counter example. In this graph, there is Euler path. There is Euler path. There is no Euler circuit. Okay, so I hope you understood. So there are few authors. According to them, option S1 will be true. According to them, option S1 will be true. So anyway, this is not a gate exam question, right? See, I told you in this exam, a lot of poor questions are there. A lot of poor questions. Okay, if you are solving questions from this exam, then you should be prepared that a lot of wrong questions you will face. Okay, is this clear? This is what I'm saying. In any good exam, we have seen the gate exam questions. We have seen the gate exam questions. They were very nice questions, yes or no? Very beautiful conceptual question. There was no ambiguity. We have seen TIFR questions. There was no ambiguity. Okay, yes or no? We have seen UGC NET questions. There was no ambiguity. In this exam, there is a lot of ambiguity. The questions are ambiguous. The questions are very, I can say, poorly framed. Okay, so anyway, the point is you don't have to worry about it. You don't have to worry about it. So remember, for this question, answer can be D also. Answer can be A also. Answer can be D or A. Is this clear? Please tell me. Answer can be D or A. For this question, I can say that what is the final answer for this question? What is the final answer? Answer can be D or A. Now it depends. It depends on the author. Okay, the question maker. It depends on the question maker. Which book this question maker has studied. Okay, yes or no? It depends on the question maker which book this question maker has studied. So anyway, the answer can be D or the answer can be A. Tell me what you will follow. What you will follow? I suggest option D. I suggest option D. Okay, because Grimaldi, Stanford, okay, in those, this is followed. This is my suggestion, option D. I hope you understood. So for this question, answer can be this also, answer can be this also. Depends on the author. It will depend on the question maker, what the question maker is thinking. But this is my suggestion that for this question, you can tick this option. Okay, this is my suggestion. Now let's move on. What about this question? This is another NIELIT question. And this is another poor question. Another poor question. This is, let me tell you why this is a poor question, very poor question. This is a very funny question. See this. The following graph has no Euler circuit because it has no Euler circuit. Yes or no? See, read this. The question is asking the given graph has no Euler circuit because it has no Euler circuit. Yes or no? Okay. So very funny question, right? Very interesting question. So this is what I'm saying. This is an exam filled with poor questions. This is exam, okay, in which you will find very, very rare good questions. I can say this is exam filled with poor questions. Filled with poor questions. If you are solving questions from this exam, then you should be careful. Okay, you should be very careful. Is this clear? If you are solving questions from this exam, you should be very careful, let me tell you. Okay, very careful while solving these questions. While solving this exam questions. Okay, because it is possible that you will get a lot of misconceptions. Okay, solving this exam questions. It is possible that you will get a lot of misconceptions. Anyway, so for this question, tell me what will be the answer? Tell me. So the question is saying the following graph has no Euler circuit because it is disconnected, right? See, this graph is given to you. This graph, this is your graph. This graph is disconnected. Yes or no? It is not connected. It is not connected. See, It has 7 vertices. That has nothing to do with this. Yes or no? Do you agree with me? It has 7 vertices. That has nothing to do with Euler circuit. That has nothing to do with Euler circuit. It has even degree. That is also fine. It has every vertex is even degree. Every vertex is of even degree. That is fine. That is fine. Yes or no? Every vertex has even degree. That is fine. You know what we need for Euler circuit? Tell me. Tell me what we need for Euler circuit. For Euler circuit, we need connected and we need even degree vertices. Yes or no? For Euler circuit, these two things we need. For Euler circuit, we need two things. It should be connected and even degree vertices. So this is satisfied. This is also satisfied by this graph. Degree 2, degree 2, degree 2, degree 2, degree 2, degree 2, degree 2. By this graph, this condition is satisfied, but this condition is not satisfied. Yes or no? This condition is not satisfied. Agree with me? So here the answer will be option C, also option D. Yes or no? The answer will be option C, comma D. Of course, option D. Of course, answer will be option D. Yes or no? Because this graph has no Euler circuit. Because this graph has no Euler circuit. Very funny option. Yes or no? It's like my name is Deepak. Because my name is Deepak. P happens because P happens. Agree with me? Yes or no? So, of course, this type of, see, if I say that P happens because P happens, of course, that is true. P happens because P happens. P happens because P happens. What are the sense of this question? What are the sense of this question, right? Yes or no? So anyway, answer will be option C, comma D. What the professor is thinking? I'm very sure the question maker is not a professor. I'm very sure. Okay, in this exam, the question makers are not professors. Okay, I don't know who make the question. I don't know, but I'm very sure the question makers of this exam, they are not IIT, ISC professors. Okay, that I'm very sure. Okay, anyway, so tell me the question maker, what the question maker is thinking? What the question maker is thinking? Let me know. I'm okay. So which option you will take? Which option you will take? You will take option C. Option to tick. Which option you will take? You will take option C. Okay, is this clear? The question maker is actually thinking option C. The question maker. This is my guess. Okay, if I can read the question maker's mind, then I'm sure the question maker is thinking option C. Is this clear? So this option you can tick. If you are attempting this exam, then this option you can tick. But anyway, option C, comma D, both are correct. Both are correct. But this is the option you can tick, option C. Okay. Is this clear? So I hope all these points are clear. So tell me, all these questions, every question we have seen every gate question, every TIFR question, every NET question, UGC NET question, ISRO question, NIELIT questions. So tell me, are you comfortable with Euler circuit, Euler path, Hamiltonian cycle, Hamiltonian path? What is Hamiltonian graph? What is Euler graph? Are you comfortable with these two topics, Euler and Hamiltonian? Please tell me. Let me know. Okay, very good, very good. So let's see this last question. Let's see this last question. Tell me, for which values of n? This is a standard question. For which values of n, Kn, Cn, Kmn have Euler circuit? So tell me, for which values this Kn will have Euler circuit? See, all of them are connected, right? Yes or no? All of them are connected, right? Okay. So Euler circuit, what do you need? You need connected also. You need connected also, and you need even degree vertices. You need even degree vertices, right? Okay. For Euler circuit, you need connected and you need all even degree vertices. These two things you need. So tell me, for Kn, what will be the value of n? The n must be odd. The n must be odd greater than equal to 3. The n must be odd and greater than equal to 3. Or I can simply say n is odd. N must be odd. Yes or no? Because when you have n odd, for example, when you have K5, then every vertex has degree what? Tell me. Then every vertex degree will be what? every vertex degree, that will be 5 minus 1, that is 4. Every vertex degree will be even. So here n should be odd. What about this? What about this? For all n, for all n, there is no problem with n. For all n, for all n, okay, there is no problem. Yes or no? For all n, this will work. This is cycle graph. This is cycle graph. This will work. C3 will work. C4 will work. C5 will work. Okay, so for all n, it will work. What about KMN? Tell me, what about KMN? Let me know. What about KMN? See, let's see about KMN. This is a complete bipartite graph. This is your complete bipartite graph. This is your complete bipartite graph. So what about this graph? What you can say? See, there are m vertices here. There are m vertices here. There are n vertices here. Okay. So this is your complete bipartite graph. What should happen? Tell me. What is the degree of this vertex? Tell me. What is the degree of this vertex? Let me know. Degree of this vertex will be m, because this vertex will be adjacent to every vertex. This vertex will be adjacent to every vertex. What will be the degree of this vertex? What will be the degree of this vertex? Tell me. Degree of this vertex will be n, because this vertex will be adjacent to every vertex. Okay. So tell me, when what we want this to be even. What we want? Tell me. What we want? Let me know. What we want? We want every vertex should have even degree. So we want that m also should be even. N also should be even. Yes or no? We want m comma n both should be even. Both must be even. Is this clear? Both must be even. So finally I can say k even. Okay, so kmn, where first of all both must be greater than equal to 1 and they both must be even. Okay, they both must be greater than equal to 1. At least one vertex here, at least one vertex here. Okay, at least one vertex should be here, at least one vertex should be here, and they both must be even. Both must be even. Means even number of vertices here, even number of vertices here. I hope you understood. Okay, so this is what we want. This is what we want. Okay, so I hope you understood all these things. So the question is also asking, what about Euler path? What about Euler path? So tell me, let's focus on Euler path. Tell me, for Euler path, what about Cn? In Cn, can you have Euler path? Remember, for Euler path, exactly two vertices must have odd degree. Exactly two vertices of odd degree. Yes or no? Exactly two vertices of odd degree. You must have exactly two vertices of odd degree. Exactly two vertices of odd degree. So Cn cannot have Euler path. Yes or no? Cn cannot have Euler path. In Cn, you cannot have Euler path. What about Kn? For which values you will have Euler path? For which values you will have Euler path? Again, here, for which values you will have Euler path? For n equal to 2. I can say for n equal to 1, 2. Okay. N equal to 1 will be trivial. See, n equal to 1, that will be trivial. That will be just a trivial case. Okay, that will be a trivial case. N equal to 1, that will be a trivial case. So you can forget about it. But I can say for n equal to 2 also it will happen. Okay. So what about Kmn? What about Kmn? Tell me. What will happen for Kmn? You must have exactly two vertices of odd degree. You must have exactly two vertices of odd degree. So tell me, which type of graph? For example, you can have this type of graph. See, you can have this type of graph. Okay, you can have here, you can have, or here you can have this. See, this type of graph you can have. This type of graph will work. Okay, this type of graph will work. Means exactly two vertices should have odd degree. So this type of graph will work. K2 comma odd. Very good. K2 comma odd. This graph will work. K2 comma odd. This will work. Is this clear? K2 comma odd. That will work. Okay. So very simple. This is about Euler path. So everything we have seen, this question also we have done. Okay, this question also done. So that's it. This is all about this chapter. Okay, so I hope you understood everything. Okay, I hope you understood every point. So Sandeep is asking a doubt. Sir, if a connected graph has cut vertex or cut edge, can we always guarantee Hamiltonian cycle not exist if you have a cut vertex? If you have a cut vertex, so let's assume this vertex is the cut vertex. If this is a cut vertex, then there is some component here, there is some component here, and there is some component here, right? Okay, there is some component here, there is some component here, if this is a cut vertex. So in this situation, can you have Hamiltonian cycle? You cannot have, right? Yes or no? In this situation, you cannot have Hamiltonian cycle, because see, if you start here, you cannot come back. The point is you cannot come back. If you start here, you cannot come back. And if you start here, you cannot go to this area. Okay, so in this situation, if this is a cut vertex, if this is a cut vertex, if this is a cut vertex, then in this situation, there is no Hamiltonian cycle. We have no Hamiltonian cycle. Is this clear, Sandeep? So if there is cut vertex, if cut vertex exists, then we can say that there is no Hamiltonian cycle. Because the reason is simple. Because you cannot visit every vertex exactly once. You cannot visit every vertex exactly once. Okay, is that clear? What about cut edge? What about cut edge? Cut edge means bridge. What about cut edge? Let's assume this is cut edge. Cut edge means bridge. Okay. So in this case, when you have cut edge, in this case, is it possible you can have Hamiltonian cycle? If this is your cut edge, if this edge is cut edge, so let's assume something is here. Okay. So if you have this edge, if I start here, I cannot come back. In this situation also, there will be no Hamiltonian cycle. In this situation also, if there is a cut edge, see this cut edge exists. This cut edge exists. Now, because this is a cut edge, in this situation also, you can notice that you cannot visit every vertex exactly once. For example, if you start here, then you cannot come back. If you start here, you cannot come back. If you start here, you cannot visit this area or you cannot visit this area. So if cut edge exists, then also Hamiltonian cycle, then also we have no Hamiltonian cycle. Okay. So if cut edge exists or cut vertex exists, then there will be no Hamiltonian cycle. Is this clear, Sandeep? So if cut vertex exists, then we have no Hamiltonian cycle. If cut edge exists, then also there is no Hamiltonian cycle. For example, you can consider this graph. This graph you can consider. This vertex, this is a cut vertex, right? Yes or no? You can note this is a cut vertex. Because if you delete this vertex, you will get two components. Right now you have one component. If you delete this vertex, you will get two components. Number of components will increase. If you delete this vertex, number of components will increase. So this is cut vertex. You can note there is no Hamiltonian cycle. There is no Hamiltonian cycle. What is the reason? The reason is simple, that if you start here, you cannot come back to this vertex. If you start here, then you cannot come back to D. See, if you start here, you cannot come back to D. You cannot come back to D. And if you start here, you cannot visit these vertices. So there is no Hamiltonian cycle. Okay. Sandeep, is your doubt clear? Anyone has any other doubt? Anyone has any other doubt? Euler circuit, Euler graph, Euler's path, Hamiltonian graph, Hamiltonian cycle, Hamiltonian path. Do you have any doubt in these topics? I hope you are comfortable with these topics. We have seen the previous year exam questions. All the previous year exam questions we have taken. Okay. So thank you, everyone. Okay, thank you.